Okay, so let's get started. Welcome to Computer Science 677, Distributed and Operating Systems. I'm the instructor. My name is Prashant Shenoy. And if any of you have any difficulty hearing what I'm saying, please let me know because I'm masked. All of you are also masked. So we are going to have some issues communicating during Q&A and during lecture. Okay, but I'm happy to make adjustments as needed. Right? The class has two sections. There is a in-class section, which is all of you. There's an even larger online section that's following along. Okay, so we'll try to make sure everybody in the class, no matter which section you're on, has an experience. So please follow the syllabus and the course policies that I'm going to discuss today so you understand what the class is about, what your expectation should be, and so on. Okay, so let's get started. Okay, so what I'm going to do first is go through the syllabus. Okay, and then towards the later part of the class, I'm going to talk about distributed systems, give you an introduction, and try to explain what this course is about and so on. Okay, so the most important link you need to know is where the course webpage resides. Okay, so that's the URL. I sent this via email to all of you. It's also posted on Piazza, so you should have no difficulty finding it. It's also on the Moodle webpage. Okay, so all the course lecture notes, links to videos, everything is going to be posted on the course webpage. Okay, so that's really your central resource as far as the class is concerned. Okay, as I already mentioned, there are two sections in the class. There's a classroom section, there's an online section. Okay, as far as the work is concerned, there is no difference. Okay, so basically think of it as one large class. Some of you come to class to get lectures, others follow along online, but you have to do the same work, same assignment, same exams, everything else is the same. Okay, just the delivery of the lectures is the only difference between the two sections. There's some seats there if you want to sit there. Okay, all right. Okay, so I want to introduce you to some of the core staff. There are a large number of them. There are 4 TAs. Okay, Ben, Chris, Hore, and How. Okay, I put their photos there so you can actually recognize them when you go to office hours or have any questions and so on. Okay, there are at least 2 graders, but maybe there may be 3 graders. You probably won't interact with them directly, but I still put their names here so you can figure out who is actually going to be assisting me with the class. Okay. Now, as far as office hours are concerned, there will be office hours every day of the week, Monday through Friday. Okay. I'm going to have office hours on Wednesdays right after the lecture. So there's going to be my first office hours today. Okay. I may add a second one on Monday, but hold off on that. I will announce all the other office hours tomorrow. Okay. And most of the office hours will be held by the TAs. Okay. But every day there'll be somebody you can talk to. Okay. Initially, all the office hours are going to be over Zoom. Okay. We are not going to have in-person office hours, but maybe 2 to 3 weeks into the semester, if the situation looks okay with respect to COVID, we will convert some of them to in-person office hours. Okay, so you can actually come see us. There will always be some Zoom office hours, so you can always talk to somebody remotely, but there'll be some of them maybe will be in person as well. Okay, but to begin with, everything is going to be on Zoom. Okay, I sent a link on via email and also posted it on Piazza as to what Zoom link to use to attend office hours. Okay, so if you need to ask somebody a question in person, please come to the Zoom office hours for now. Okay, so textbook, there is no textbook for the class. Okay, all the textbooks that are out there are pretty outdated at this point. So there's no point having a real textbook. So we'll provide course notes so you can figure out what's going on in the class using the notes. And there are 2 suggested references. They are the old textbooks that we used to use for the class. Okay, neither of them is mandatory. Both of them are available for free as PDFs legally. Okay, so you can go to the author website, get the PDF copies, and then use that as a suggested reference. Okay. So please take a look at the links, go get your copy, use that as suggested references. Okay, but you don't really have to buy anything as far as the textbook is concerned. Okay, so as far as the course contents are concerned, okay, there's a list of topics we are going to cover in the class. Okay, today we are going to do an introduction. Okay, very basic introduction to what is distributed systems, why we should care about distributed systems, and so on. Okay. Then subsequently, we are going to talk about distributed architectures, broad architectural principles for designing distributed systems. Okay, then we'll talk about inter-process communication. We'll talk about processes, scheduling, using virtualization for scheduling, and so on. We'll talk a little bit about naming and location management. Okay, and then we'll spend a good third of the class talking about what I call canonical problems in distributed systems. Okay, so these are problems that you will encounter in a wide range of distributed. So we'll consider them in the abstract. Okay, we'll try to understand how to solve these problems. That's everything from mutual exclusion, leader election, synchronization, consensus, and so on. Okay, so we'll look at all of them. Okay, and then we'll also see where to apply them. Okay, so we'll study them in the abstract, but we'll also see applications of most of these problems. Okay, that's really the crux of what people consider distributed computing. Okay, these are the main concepts that underpin the design of many distributed systems. Okay. And then we'll move on to talking about resource sharing, how to replicate, how to ensure consistency in large distributed systems. Okay. And then towards the end, we'll talk about fault tolerance, security if we have time, okay, and middleware likewise. And then a few advanced topics. Okay. One of which is something that we'll talk about well earlier than towards the end, which is going to be cloud computing. Okay, so that we'll cover not at the end, but maybe more at the beginning. But then we'll also talk towards the end about web, green computing, multimedia, mobile systems, to the extent we have time. Okay, so some of this is going to depend on how much time is left at the very end. Okay. Okay. Any questions on this so far? If there is a particular topic you really love for us to cover, send me a note or raise your hand. Happy to consider any suggestions on what we should talk about that's not covered here. Okay, some of this can be what people want to actually understand or take away from this class. Okay, course grading, as far as concerned, there is going to be multiple ways you are going to be evaluated. Okay, so the most of the course is going to be in programming assignments or what we call labs. Okay, so that's around 50% of the grade, approximately 3 labs. Okay, maybe there is a 4th lab, but sometimes we combine it with one larger lab. Okay, most of the labs you can actually do in groups of 2. Okay, no more than 2 groups of 2. You can of course do them individually if you so wish, okay, but we will allow you to do them as group work. Okay, that's the only thing that you can actually do as group work. Everything else in the course is individual work. Okay, that's going to be homeworks and exams, clearly. Yes, homeworks are 8% of the grade. We'll have an homework approximately every 10 days. Okay, maybe I think 5 or so homeworks. Okay, over the course of the semester. There's going to be 2 exams, 1 midterm and 1 final. Okay, that is going to be 40% of the grade. Okay, the midterm is an in-person midterm. Okay, that's going to be held in class. March 25th is the date that we have scheduled the midterm. Okay, we'll put all of this information up, so you don't really have to worry about forgetting it. But I just want to tell you now that the midterm is going to be after the spring break, not before, just so that you understand when it's going to happen. Okay. The final exam is, of course, at the end of the semester. Usually, it's a take-home exam. Okay, so midterm is in person, finals tends to be take-home. We'll try to do the same thing this time. Okay. And then there is a small amount of grade that we have reserved for class participation. Okay, you can participate in any number of ways. Okay, for the in-class section, the best way is to actually ask questions and have discussions when we have lectures. Okay, but there are a number of other ways you can participate. You can actually have discussions on Piazza. Okay, ask questions, answer questions, so that there is actually some active exchange of information between all of you and the instructors and the core staff. Okay, there will be other ways to participate, including a small weekly quiz Okay, the weekly quiz is actually meant for the online section, but the in-class section also has to take it. At the end of each week, okay, we'll have a short quiz. Okay, maybe 2-3 questions, very short, almost multiple choice like, but maybe have short answers. The main goal is not to evaluate you in any way, but to ensure that you are following along. Okay, the course is recorded. Okay, all the lectures are on YouTube, so it's entirely possible you think that you don't need to come to class if you're in the in-class section, or if you're in the online section, maybe say, I don't need to view the lectures, I'm going to just do it before the exam, and then you fall behind. Okay, this is simply a forcing function for you to review each week's lectures in that week and then take the quiz. Okay, because you won't be able to understand what the quiz is if you haven't viewed the lectures. Okay, so it's a very low overhead thing, but it's something that I have found allows you to keep up with the class, because the material that we are going to cover will pick up pace. Yes, we'll start slowly, but then you'll see that the pace picks up, and if you don't keep up with the class, you fall behind. Okay, so the whole goal of the quiz is just to prevent that from happening. As you can see, it's less than 2% of the grade. Okay, so it doesn't really cost you much, but it keeps you on track. Okay. Now, prereqs, as far as prereqs are concerned, typically you need to have some knowledge of an undergrad OS class. Okay? We do not make that mandatory anymore, because some of you come from other backgrounds, not from a computer science undergraduate. And that's okay. But we still assume that you'll know something about an undergrad OS class. Okay? If you know nothing at all but what an operating system is, you may not actually be prepared to take this class and succeed in it. Okay? But if you've forgotten about what an OS is, or it has been a while since you took that class, I can recommend a book that is also openly available. It's a textbook that is used in our undergraduate class. Keep that with you, read it, so that you have the concepts covered. Because I'm not going to review all the undergrad OS concepts when I talk about a more advanced version of them. Okay? So I'm assuming some basic knowledge, but we will not enforce anything. So you can decide if you have any issues, come talk to us, whether you are the right background and so on. Okay? Now, the other prereq is that, of course, you need to have good programming skills, because half the grade depends on it. All the labs require you to program. Okay? So you need to have some programming skills. The language is a little flexible, because this is a graduate course. We are not going to mandate that you write everything in Java, you write everything in Python. We'll let you choose. Okay? Not arbitrarily choose whatever you want, but we'll give you a choice of maybe 2 or 3 languages that are reasonable. Typically, it's like Python, Java, and C++, or something along those lines. Okay? And then you can decide what you use to design your code. Okay? But you need to be proficient in one of those languages in order to succeed. Okay? Because half of your grade is going to depend on it. Okay? So those are the 2 prereqs that you need to have in order for you to have a good experience in this class and succeed. Any questions so far? Yes, please.
So can people in the online section and the discussion class section make groups together?
Okay, the question is for group assignments, can somebody from an in-class section team up with somebody in an online section? The answer is yes. As far as we are concerned, there's one big class. Okay, we don't distinguish between who you team up with, who you work with. So long as you have a partner you can work with well, you can team up with whoever you want. Okay, there's no restrictions.
So both are same, like one has to be on the YouTube and everything is the same thing with the assignment.
Right. So the 2 sections are going to be, the question is, are the 2 sections identical in the work? They're absolutely identical. Okay, all the homeworks, all the exams, all the deadlines, everything is identical. Okay. The only thing is, if I just make one section, then we'll have to have a giant room with 200 seats in it for the class to work, which gets harder. Okay. So we always have some students following along. Okay. So you can team up with whoever you want. Yes, please. Question. Okay, that's a good question. So the question is, if you are actually watching online, can you ask questions online? We are trying to work that out. Okay, I do want for people who are following live to be able to ask questions. Okay, what's the exact mode? I have to figure out. I don't want the questions to be publicly posted on the internet, so we'll try to figure that out. But of course, if you are watching the recorded lectures, you can always ask questions afterwards. There's Piazza. There are many ways to do that. Okay? But live Q&A, for somebody who's following along for live lectures is something we're just trying to figure out. Okay, give us a little time. The short answer is we would like to have that happen as well. Okay. Any other questions? Yes, please. What is the schedule for the midterm for the online section? Is that what you're asking?
Yes, like in person classes to come live.
Yeah. So the midterm exam, even for the online students who are on campus, okay, on campus students, the online section will take the midterm physically in a large classroom along with this section. Okay. There are a small number of students who are in the online sections who are actually remote. Okay. And we'll make arrangements for them to have live proctoring. Okay. They'll be taking a proctored exam over Zoom. Okay. Either way, they're going to take an exam live, okay, in the same amount of time that everybody else takes. Okay. Any other questions? Okay, so let's move on. Okay, so the number of tools that you need to be aware of. Piazza is what we are going to use for Q&A. Any questions of any sort, technical or logistics, you go there and post. Okay, there's also a way there to ask for exemptions. If for any reason you come down sick, likely to happen this semester for some of you, hopefully not, but always a possibility. Okay, that's where you go and ask for accommodations that you need more time or something like that. Regrade request, there's a way to use Piazza to make them. So we streamlined all of these things. Okay, so you don't have to email me because the email volume for a large class is so large, it's occasionally possible to miss something. Okay, so we're going to use streamlined ways by which you make requests. And of course, the rest of Piazza is the same. You are going to ask questions about technical things and we're going to answer them and we'll have discussions and so on. Okay, so keep that in mind. We are going to use Gradescope to turn in your homeworks, okay, and GitHub Classroom for you to turn in your code programming assignments. Okay, so you probably use some of these tools in other classes as well. We are going to use the same tools here. Okay. Now, as far as GitHub Classroom is concerned, I already put out Lab 0. It's not a graded lab. Okay, it's just for you to actually go there and link your GitHub ID to your class roster so that we know who you are. Okay. So you probably have seen an invitation. If not, go to Moodle. There's a link to accept Lab 0. Okay, go to Lab 0, link your GitHub ID. Rest of that Lab 0 is just what is GitHub. If you know GitHub, you don't really have to do that lab. Okay, it's ungraded, but please do that soon so that everybody is actually on GitHub Classroom. So your GitHub ID and the roster are connected. Okay, that way we know who you are. Okay, and then web page I mentioned, YouTube channel already mentioned that as well. And Moodle is a tool we'll use, but really mostly use an online gradebook because the course material is on the web page. Assignments are coming in through Gradescope or GitHub Classroom. Yeah, but we'll use Moodle to pull it all together for grading. Any questions about any of these? Okay. Course policy. Okay, so first thing is mask policy. All of you are masked. That's good. Please continue to do so. I will always bring some masks here. If you forget, just ask me for one. I'll give you one. Okay, but don't come and stay here without a mask. Okay, that's not a good idea in the midst of a pandemic. Okay, device policy I already mentioned. I prefer that we don't have any device usage during class because usually you get distracted. You start doing something else. You lose interest in the class. You've taken the trouble to come here, spend an hour listening to what we have to say and participate. Okay, there's no attendance. So if you don't feel that you're interested in the material, you can just view the online lectures later on. Okay? But if you come here, please come without a device so you can participate well. Okay, I will put up the course slides before the lecture, so you can even print them and bring them here and take notes. Okay, so that way you can actually have a good experience with whatever is happening in class. Okay, the other thing I wanted to mention is as part of class participation, we need a set of scribe volunteers. Okay, scribe essentially takes notes during the class and then makes it available to everybody else. Okay, only 24 or 23 lectures, and there are 150 students. So not everyone can be a scribe, but I would appreciate if at least 23 of you volunteer to be scribes so that everyone can benefit from what. If you're interested in being a scribe, please sign up, and then we'll send you instructions on how you type up your notes and send it back. And in return for doing this, we'll give you a small percentage for your class participation. Okay, so you actually get something for the effort you put in. Okay. Okay, so that is it as far as the syllabus is concerned. I'm going to take a few second break, see if there's any questions about the course logistics. So now we are going to switch gears, talk about introduction to distributed systems. Any questions or concerns about anything I've said? Yes, please. Okay, question is you give a brief introduction about the programming assignments. Yeah, so we haven't designed them yet for this session, but by and large there are 3 labs. Okay, each one builds a little bit on the previous lab, not entirely. Okay, but they roughly match the concepts you are learning in the class. Okay, so the first one is client server programming. So you'll write a program that has a client version, there's a server that runs somewhere else, there's inter-process communication, you may use RPCs, you may use RMIs, you may use concurrency to ensure. So this is like a web browser and a web client kind of system. Okay, so that's the first one. The second one typically makes the server part of the application more complex. Maybe you do replication, maybe you do something else based on whatever we have learned in class. So essentially, this is how you actually build a web application in the cloud or something along these lines. Okay, and part of that might involve that you containerize your application, you put it in Docker and deploy it somewhere on a server and things of that sort. So you get to know how things actually work in the real world, maybe at a much lighter level. You're not actually going to do large-scale deployment. Okay? And the third one builds on that. You can add fault tolerance, you can add consistency, all these advanced concepts. If some nodes go down, can your application continue to work? By and large, these map to the concepts we are going to learn. Okay, so that's how the assignment will be structured. We haven't exactly decided what the assignment will be yet. We'll know in a week or so. We're still designing that, but that's been the case for the past several years. Okay. Any other questions? Yes, please. Okay, will we be learning any DevOps? So the short answer is yes. Okay, as part of this, you will learn about virtualization, you'll learn about Docker, containerization, Docker deployment, a little bit of AWS. Okay? We have to still figure out how to make that work, make sure everybody has access to a cloud system. But yes, that has always been part of it. Yes, and that will still be the case. Anything else? Okay, could you use your own cloud system for homework? Potentially, yes, but we'll have to understand what that means. Okay. Okay, so let's move on. Okay, if there are other questions, please ask on Piazza, and there are many, or come to office hours. Okay, so what we'll do now is talk about what is the distributed system and why do we need to study distributed system. What should you expect really to get out of this class? Okay, so the reason we want to think carefully and understand and study distributed systems is that most systems you encounter on any computing system today tends to be distributed in some shape or form. Okay, the web is a large worldwide distributed system. Many of the apps that even run on your smartphones actually are distributed because there is a server component somewhere else. Okay, what you are actually interacting with on your phone is the client side of that application. There's a server side that might be residing on a cloud or some other machine somewhere else on the network. Okay, so practically everything that you encounter today, whether it's the World Wide Web, whether it's a Google search engine, cloud computing systems, any e-commerce site that you go to, whether it's Amazon or a news site, CNN, take whatever site you want, all of them are distributed. There are many peer-to-peer systems that we'll study in the course of this distributed systems class that are also distributed. We'll talk about cluster computing, network computers, and so on. So because these systems have become pervasive, it's good for us to understand what they are, how they work, and importantly, how to build them well. Okay? As we will see, designing distributed systems is a lot more challenging than designing a single standalone program that you might write. Okay? There are a lot more things that you need to worry about for your system to work well. Okay? So the principles of how to build good distributed systems is what we will study. So you get an understanding of how some of these systems are actually built and operated. Okay? So that's a motivation for why we want to study distributed systems. So we are going to cover basic principles. Okay? These principles you can apply to a small scale distributed system, maybe 2 machines, client and a server, or a very large one, okay? Tens of thousands of machines distributed all over the world. Okay? The principles are similar. Okay? So it's good to understand what they are, how to make them work, and so on. Okay? So with that very quick motivation for why we want to study these systems, let's look at a definition. Okay? What is a distributed system? We'll start with a very basic definition. Okay? So we'll say that from our perspective, a distributed system is one that has multiple connected computers or processors that work together. Okay? So the second bullet gives you a nice definition saying it's a collection of independent computers that appear to its user as a single coherent system. Okay? So there are multiple machines in any distributed systems. They're connected by a network. They work together to achieve some common task, which is to implement an application of some sort, and gives to their users an abstraction of a larger entity. So you sometimes may not even know that there are multiple machines involved in implementing that application. Okay? That's a very simple definition, but it's a broad one. Okay? It will encompass lots of different kinds of systems that we'll encounter. Okay? From this perspective, even a parallel machine, a machine that has multiple cores, multiple GPUs, okay, will also be a distributed system of some sort. Okay? And so will entities that involve lots of machines. Okay? So it's a simple but broad definition, and that's the one we will keep in mind as we progress through this course and try to understand different kinds of distributed systems. Okay? Any questions on the definition here? Okay, so now let's take a look at some advantages and disadvantages of distributed system. What do you gain when you make a system distributed, and what do you lose, or what are some drawbacks? Okay, so some of these you may not understand or appreciate yet because you don't know as much about distributed systems, but as you get a much better understanding of them through this course, you will understand why some of these actually matter. Okay. The first advantage is that resource sharing is possible. Okay? Resources that reside on another machine now can be accessed by a different machine. Okay? And you can think of any number of examples, right? Cloud storage, your Google Drive. Okay? You are actually accessing disk storage on a different machine. Okay? That's resource sharing. That's a very simple example of what resource sharing means. Okay? You no longer are limited by the storage on your machine. Now you can actually use storage on some other machine. That's an example of resource sharing. Okay? There's economic arguments of price performance ratios. Okay? So if you make a system distributed to make it bigger, rather than making a centralized system bigger, you actually can get that performance at a lower price. Okay? So what that typically means is if you want to run a large application, you have 2 ways to do it. Okay? You can buy one large centralized machine and run that application there. Okay? Or you can distribute that application over a collection of smaller servers. Okay? And often the latter gives you an advantage in terms of price performance because centralized machines that are large are actually more expensive than using commodity servers that are networked together. Okay? So that's a price performance argument for distributed systems. Okay? We'll also see that you will actually have a reliability advantage. If you build your distributed system well, okay, even if some nodes in your system go down, your application as a whole continues to function. Okay? That's a reliability argument. Of course, if you do not build your system well and there are single points of failure, okay, you can actually get worse reliability. That if a node goes down and maybe 100 other servers are up, yet your system just stops working. Okay, so you got to do this well, but if you do it well, you get a reliability and potentially also scalability benefit. Okay? And last but not least, there's potential for incremental growth. Okay? So what that means is, as your application grows over time, so can your system. Okay? When you deploy your application on day one, you don't have to deploy it on the largest possible system that you ever want to serve your users someday. Okay? You can keep growing as your users grow. Okay? Think of a game, an online game. Okay, there are lots of games that game developers write. They don't know which one is going to be a hit and which one is just going to have some mediocre popularity. Okay? So you don't know the number of users who are going to access your game the day you write it and put it out. Okay? So what size machine are you going to put this out on? You don't know. You just have to make some guesses and say, I'm going to assume that there will be 1,000 users. Okay? And you put it on a system accordingly. Maybe your game becomes really popular. Okay? And suddenly it starts growing in number of users. And now you can grow your system as your user base increases. Okay? That's an advantage because you can keep adding machines. If you had a centralized system, you can't just make the centralized system bigger. You have to throw it out and put it on a different one. That's a bigger machine. That you don't have to do here. That's called incremental growth. Okay? So those are all benefits. Okay? But there are some drawbacks as well. Okay? The biggest drawback that you can think of is writing applications is a lot more complicated than in a centralized system. Okay? If you write a single Java program, you don't really have to worry about other components of the program. Everything you need is in one program that you write. Okay? But you write a distributed system, you have to write multiple components. There is at least a client and a server component. There may be many server components, not just one. If you have a peer-to-peer system, there are lots of peer components. How do they all work together? Okay, how do you debug such a system if something is not working? Okay, all of this gets more complicated. Okay, so you now need to make your programming languages adapt to distributed systems. You need to make your operating systems have features that allow these distributed systems to run. So that basically comes with higher complexity in your software stack. Okay, everything from the OS all the way to the applications needs more functionality for distributed systems to work. Okay, so that's a drawback. Okay. Second drawback is network connectivity is essential. Okay, without a network, your system will not work. Okay, because our definition said it's a collection of machines that are connected together over a network. Okay, if the network fails, then you don't have a distributed system that functions anymore. Okay, if part of a network fails, the rest of your system can run. Okay, but if there's a single point of failure and something fails, then you're out of luck. Okay, so that's something you want to keep in mind. And security and privacy are also big problems. Okay, now your application is accessible to someone on the internet. Okay, so they may be malicious users who are trying to hack into the system. Okay, if your system is not networked, it's just centralized, you don't have this problem. Okay, you just run things on a machine and that's it. Okay, but whenever you network something, you have to worry about security, privacy issues as well. Okay, so these are all things that are going to become more complicated. Okay, but hopefully the advantages will far outweigh the disadvantages. So this is still a good way for us to build our systems. Okay, any questions here? Yes, please. Okay, so there's a question about what scalability means and what incremental growth means. I'll talk about scalability in just a moment. There's a reason I didn't mention this here, because I'm going to compare scalability and contrast this with centralized system. We'll talk about that. But incremental growth I can address now. So what does incremental growth mean? Incremental growth simply means that the size of your distributed system or application has to grow over time because the workload it is servicing is growing over time. Okay? The reason the workload might grow is more users start accessing the system, or simply there is more work to do. Okay? And as that growth occurs over time, you can actually scale your system. So the day you deploy your system, you don't have to size it for the largest possible user base it will ever service over its lifetime. Okay, the assumption is that the system will evolve as the workload evolves, and you can incrementally grow the system. Okay, that's an advantage of designing things in a distributed manner or a centralized manner. Okay, any other questions here? Okay, so we'll come to scalability in just a moment, but let's talk about transparency for just a second. Okay, so what does transparency mean? First of all, the slide has a lot of material, but I'll stick to the basics. Okay, transparency just means that you are actually hiding something from the user. Okay, now when you build a distributed system, you don't want to expose every single detail to the user. You want to only expose the right set of things and hide the other complexity, because I already said these systems are very complex. Okay, so the question is, what do you expose to the user and what do you hide from the user? Okay, and is best understood with an example. Okay, let's take the Google search engine. Okay, what's the interface that it provides to a user? The search box. Okay, what do you know about what is actually happening when you type in a search query? Almost nothing, other than you get a response back. Okay, so they have hidden everything from the user. The fact that there is a search engine that might be running on tens of thousands of machines, the fact that your search query might go to a certain machine, all of this is hidden. Okay, user doesn't need to know. User just wants answer to their question. Why do they care whether it's machine number 100 or machine number 513 that's answering that question? They don't need to know, right? So this is an example of transparency, where you have hidden the fact that there is lots of machines that are actually servicing all the queries that are coming in, which machine services, how does your query get routed to a particular machine, and which machine services is. All of that is hidden. Okay? Now there are many such properties you can hide from the user for the system to become more useful. Okay? And so that is what is listed here. Okay? So what are the various properties of a system that you could potentially hide from a user? And we'll take a few. Okay, so here is one. Let's take location transparency. Okay, it hides the location of a resource from the user. Okay, again, I'll explain this with an example. Okay, so let's say you type in a URL. Okay, let's say you say www.facebook.com. Okay, now this URL doesn't tell you where the machine is located. Okay, it's just a convenient handle or a name for you to access a service, which in this case is a social media site. Okay, where is it located? Okay, all of that is hidden from you. Okay, that's called location transparency, that the name of a resource does not reveal the location of that resource. Okay, now there are other examples where that may not necessarily be true, that you might actually need to expose the details of a location. In certain services, you might say, I need to access a service that is in this country versus some other country, and so on. So in that case, there is some location information that gets embedded. Okay? But in many cases, that's hidden from you. Okay? That is called location transparency. Okay? Replication transparency, I already explained using our search box example. The fact that the service was replicated was hidden from you. Okay? You just have an interface that just allows you to interact with the system. The system just looks like a logical black box. You have no idea what's in it. You're just getting answers. Okay? That's basically replication transparency. There will be some other kinds of transparency. Failure transparency is a good one. Okay? The fact that some elements of your system are down is hidden from the user. If something goes down, the system transparently starts sending work to other nodes that are still functioning. Okay? So the user doesn't see the impact of a failure. Okay? As opposed to most of the time, something goes down, the website crashes. You don't actually see this often. Okay? But well-designed distributed systems will provide failure transparency. They will have replication, and when some nodes go down, other replicas take over that work. Okay? So the user doesn't see any impact. Okay? So there are other properties here. I'm not going to go into all of them because we don't actually have the background yet to delve deeper into them. As we progress, we'll come back to some of these. Okay, but the idea is when you design distributed systems, okay, you want to ensure that certain complexities are hidden from the user. Whatever the user needs to know should be exposed, and whatever they don't need to worry about should be hidden. Okay? That's a good way of designing these systems. Okay. Now let's talk a little bit about open distributed systems. So what do these mean? Okay. Many systems, that if they are called open, will expose their interfaces to others, to other clients. Okay. So they will publish their interfaces. So you can now write your own clients or other components that interact with that system. That's one way of saying a system is open. Okay. Let's take an example. Okay. Take Google Maps. Google Maps has an open interface. Okay. You can actually use that interface to embed a map on your web page. You can write your own mapping client. You can send requests and it can send you back in mapping information because the API is published. The interface is published. So long as you have a token to access the service, you can call methods and the service will respond to you. Okay. So that's an example of an open system, one where the interface is open. Okay. There are many degrees of openness. Okay. The most open kind of system is an open source system where the source code is open, the interface is published, everything is known. Okay. So that's the one end of the spectrum where the code, everything is open. But often when people say something is open, they're actually only referring to the interface, okay, of the system being open. That allows you to write other components that talk to each other and build other services. Okay. An open source distributed system is one where even the code is available. But by open, we are here, all we mean is that the interfaces are specified and published. Okay. This allows for interoperability and portability. Okay. It also allows for extensibility because you can write layers of software on top of that interface and expose other interfaces as well. Okay. You can use the basic Google Map interface and write other applications. You can write Yelp, okay, which is now going to provide you restaurant reviews, but it has mapping information in it as well. Okay. So there are many examples of this sort where you can take one service, build on it, and make another service. Okay. So that is a good way also of designing systems. Okay. This has nothing to do with what you hide or the transparency. It's just how you build your system. Will you allow others to work with your system in some way? Okay. Or will you hide those interfaces? Yeah. So now let's come to the scalability question that was asked. So to understand the scalability advantages of a distributed system, it is worthwhile contrasting a distributed system with a centralized one. So there are many kinds of a centralized system. Okay, there are three that I've listed here. The second and the third are just flavors of the first one. Okay, centralized service essentially means that there is a single server for running an application. Okay, the code for that application resides on that server. The data for that application resides on that server. Okay, so the application is essentially limited by the resources of that server. Okay, the workload on the server saturates the CPU, it uses up all of the memory, or it uses up disk storage, then you are not going to be able to scale it beyond that. So there are limits to how much you can scale an application based on what centralized server it runs on. This is a centralized application or centralized service really that we are talking about. Okay. So any centralized service is limited by the resources of the machine that it runs on. Okay, you can imagine if you had a game server example that I was talking about, if you have lots of users, okay, and that server just gets overloaded, you're out of luck. You cannot take more users in your game. Okay, if you really want to make a lot of money off your game, you better not make it centralized if you have lots of users. Okay, you want to make it distributed in that case. Okay, now if you tease apart what actually is causing the bottleneck on that centralized server, you come up with one of two things. Okay, it's either that your data is centralized and there's a lot of data access, and that is the bottleneck that prevents your machine or your application from scaling. Okay, or your code and the algorithms in the code are centralized, and basically they cannot handle the workload that they are seeing, the number of users that might be accessing the service. Okay, so essentially any centralized service will also have centralized data and centralized algorithms, and one of the two is actually going to be the real source of the problem. okay, depending on whether your application is CPU intensive or data or IO intensive. Okay. So essentially, you do not need for a system to be distributed for your data and the code to be distributed. You can have distributed systems where your algorithm is distributed, but the data is centralized. Okay. Many web applications are built this way. They have a single database. Okay. But there are multiple servers that have code running in them that all access that database. That's a distributed application where the code is not centralized, the code is distributed, but the data is centralized. Okay. You can also do the reverse where the data is actually on many machines, but the system may not be centralized. And the more general case is where both the data and the code is actually distributed. But there are many flavors, as you can see, depending on whether you're talking about distributing the data, distributing the code, or both. Okay. But as you can see, depending on what bottlenecks arise, you are going to have scalability problems whenever you have any element of your system that is centralized. Okay. And if you want to scale to a larger number of users or scale to larger workloads, you essentially have to remove that bottleneck by making that component distributed. Okay. And if you do that, then you are going to get scalability benefits of your distributed systems. Is this clear? Any questions on this? Okay. Okay, so now let's talk a little bit about scaling techniques. Again, all of this is introduction, right? So we are going to come back to this and look at all of this in a lot more detail. It's just to give you a flavor of what are distributed systems and their benefits and so on, in a little more detail than what I presented in the introduction or the definition slide. Okay, so scaling technique. How are you going to scale? Okay, we don't like a centralized system because of its lack of scalability. What are things you're going to use to actually make them distributed and start scaling? Because there are many things you can do. Okay, so I've listed some of them here. Some of these things will not actually make sense at this point in time because I have not even introduced some of the terminology, but I'm going to mention it anyway. Okay, so first thing about distributing an application and scaling it is to essentially take the state that you keep and you put it on multiple machines. Okay, simplest example of state is the data or the files that you have. Okay, that's an example of state. You can also have memory statelets, but we'll not worry about that here. So you take your files, you take your data, you distribute it across multiple machines, and then when you're trying to access that piece of data, that machine services it. Okay, that's an example of how you can actually scale. Okay. Now, the second thing you can do is make decisions based on local information as opposed to global information. Okay. Because your application now runs on multiple machines, each machine has some piece of knowledge about what the application is. If you want to make decisions, you don't want to ask every machine what they know in order to make that decision. That is immediately going to create a scalability bottleneck. Okay, as much as possible, when a request comes in, you want to service it based on your information that you have as a machine, as opposed to having to coordinate with lots of other machines. The more coordination is needed, the worse your scalability is going to be. Okay, and we'll see many examples of this, okay, throughout the course. Okay, so there are examples like even when you do distributed training of machine learning models. Okay, when you're training a model, okay, you have multiple client machines that are all processing data. They all have to communicate with one another to compute their gradients. There's more communication overhead, okay, as opposed to they send all the gradients to a centralized server, parameter server that aggregates them and sends them back. Okay, which of the two is more scalable? Depends on the communication overhead. Okay, the more communication, more coordination, the less scalable it actually becomes. Okay. Now, if you don't know what machine learning training is, which is not that you something you have to know about for this class, don't worry about it. But if you know, you understand what I'm trying to say. Okay. Now, yet another scaling technique is to ensure that there's no single point of failure in your system. Okay. So what that means is if any component of your system goes down, the distributed system as a whole continues to function. No single point of failure. Often very hard to achieve. Yeah, as you can imagine, you probably read press stories where Amazon makes an error on one small thing and the entire cloud system goes down. Okay. That tells you that there are always, no matter how hard you try, some single point of failure somewhere. And if that goes down, the entire system goes down with it. Okay, so there are large repercussions if there are single points of failure in your system. As much as possible, you want to avoid that from your system. Okay, but as we've seen, it's actually much harder to practice that principle. But it's a good one to know about. Okay, and the last one is called no global clock. Okay, this basically means that there should be minimum synchronization over it at this point in time. We'll define what a global clock is much later in the class. But for the purposes of today's lecture, this just means that if you don't have to synchronize as much, you are going to actually have more scalable systems. It's similar to saying I don't want to communicate or coordinate as much. Okay. Now, what are some techniques that you can use to essentially implement those principles? So first one is asynchronous communication. The more synchronous you make things, the more blocking there is going to be, and then there's going to be essentially performance impact. So the more asynchronous techniques you use, whether it's asynchronous programming or asynchronous communication, the more scalable your system will be. Okay? Again, if you don't understand asynchronous communication or programming, we'll get to that. Okay? But if you know what it is, at least you understand why this is actually important for scaling. Okay? Distribution of data, distribution of code, we already talked about. You don't want to have centralized databases, data structures, centralized algorithms. All of that are going to prevent your system from scaling. The more distributed you make it, the better it will scale. Okay. And last but not least, you can also use caching and replication as ways to further scale the system. Okay. Caching is always a good thing that people like to add in distributed system. It speeds up access to frequently accessed items. Okay. And replication just allows you to have more machines to distribute the work. Okay. So both of these are very common scaling techniques. Okay. Any questions on this? Yes, please. Okay. So question is, what does it mean to say no machine has complete state? Okay. So this is essentially a principle that says that you don't want centralization. It's a sort of a crude way to put it. State in this case, one way to think about state is data. Okay, because data is a type of state. So if you're building a distributed system, you don't want to actually say that every machine has access to all of that data. You might say, I take my large database and I say, I partition it into smaller pieces and say, you are responsible for this piece, you are responsible for this piece, this other machine is responsible for some other piece, and so on. That's the way you're distributed, okay, as opposed to putting it all together. Okay. So that's an example of what it means to not have complete state. We'll get to what state means. State is more subtle than what I just said, but this is an example of what it means. Okay. Other questions here? Okay, so we are going to switch gears now. This was just a quick definition of distributed systems, advantages, disadvantages, contrast that with centralized services and centralized techniques. Okay. I'll switch gears and talk a little bit about history of distributed systems, okay, in 2 or 3 slides, not like a real history that you would want to go and look at, but something that gives you a flavor of how they've evolved. And I will talk a little bit about operating systems. Okay. Part of this course also deals with operating systems. Okay. We are particularly interested in distributed operating systems or operating systems that are actually designed to serve distributed systems, but it's good to understand how they have evolved as well. Okay. So let's start with first distributed system. Okay. So what kinds of architectures have they used? What did early ones look like? Okay. Maybe 50 or so years ago, or maybe even more than that, the early distributed systems used what was called a mini computer model. Okay. A mini computer, think of a mini computer as essentially one server to which multiple users have connected their terminal or a keyboard. Okay, so you can essentially communicate with that machine. That machine might have a network connection to some other machine, and essentially that's how you build your distributed system. Okay. Earliest example of this was email. Okay. You essentially, to send an email, which is really a message, you connect it to your local machine, you send gave an address, you wrote some message, that machine would then connect to some other machine and just copy that message over. Okay, and that's essentially how email grew. So that's a very early example of a distributed system. Okay. Now, as machines started getting cheaper with technology improvements, okay, distributed systems started getting more popular. Okay, and that basically happened with what is called the workstation model. Okay. In the early days, it was not possible for a company to provide a machine to every one of their employees. Computers were just too expensive. So you would have one bigger machine, because a mainframe or a mini computer and terminals connected to it. But as hardware costs started falling, you could essentially afford to give every user a workstation. A workstation is like something that essentially became PCs later on, but they were Unix workstations, essentially were like machines that you could have on somebody's desk. They were more powerful from a user's perspective because you had local computing. Okay? And the advantage of workstations was you could also put them on a local area network. They could all communicate with each other. Okay? Now, this model allowed you to design lots of these early types of distributed systems, like distributed file system that we look at. Okay? So you could say, why can't I access a disk on somebody else's machine and access those files? Okay? So that basically led to designing distributed file system. Or you could say, that machine is idle. Can I run my job there? Because I have lots of work to do. My machine can't run all of them. So can I actually run some jobs on idle machines? Okay. So that was another example of distributed computing. So this workstation model allowed you to build a whole new types of distributed applications and distributed systems. And this is really where the field really took off in the early to late 80s. And then there's been a lot of evolution since then. Okay, then basically that brought the client server model, where rather than having a pool of workstations, you had some machines that were more powerful. We called them servers, and all the other workstations became clients. So rather than running jobs on somebody else's machine, you essentially ran jobs on some larger machines called servers. Okay? So that basically led to the client server model. Okay? And there are many examples of that. And the web is also an example of that, although the web evolved a lot later than the early client server computing. Okay? And then as servers also became more powerful, you did not need to have one, you could have a pool of them. Okay? That led to what is called a processor pool model, where there was a pool of machines, okay, and there were users that were submitting work to that machine. Okay? And you probably are familiar with this model if you used a cluster of any sort to do your computation. So that's a collection of servers that provides a service. You can just submit jobs to that cluster, and one of the machines will run it for you. Okay, so you essentially take advantage of a large pool of processors. Okay, so that's our processor pool model, which has now grown into a cluster computing model. Because the cluster computing is essentially an evolution of this early model, which was called a processor pool model. Okay, so we have cluster computing, which has now led to also the data center computing. We'll get to all of that. Okay, when you connect clusters across wide area networks, you have what is called a grid computing model. So these are large clusters, but they're connected over the internet. Okay, so now you essentially have a logical collection of a much bigger cluster, for where each component of that larger cluster is actually an individual cluster. Okay. So this is essentially called grid computing, also called wide area clusters. Okay. And many of the cloud computing infrastructures essentially are like that, or built like that. Yeah, and so now essentially that's all led to what we call cloud computing. It has all of these features built in. Okay. Just a natural evolution as technology has improved, as you can buy more servers for the same amount of money and whatnot. Okay. And this evolution has continued. It hasn't stopped at cluster computing. Now, essentially, computing is, or hardware is so cheap, you can put computing everywhere. Okay. Your phone has maybe a 4-core or 8-core processor in it. Okay. Things that you don't think of as computing devices essentially are computers. You buy a TV, you can only buy smart TVs. Okay, it essentially runs Linux inside. Okay, it has a processor, it has a network, it has Wi-Fi, it can run apps, just as your phone can run apps. Okay, you don't think of a TV as a computing device, but it's not only a computing device, it's a distributed computing device because it can start streaming stuff from all kinds of streaming services. Your car is also a computer. Okay, and I don't mean self-driving cars. I mean cars that we drive today. Okay, if you actually look at it inside, it essentially has a LAN. It has all kinds of microcontrollers that sense things, they control things. Okay, they communicate with each other. Okay, so there's essentially an entire network infrastructure inside every car. Okay, but you don't think of them as a computing device. Okay, so practically everything that technology that we use today essentially has computing device. It has communication or networking capability, and it's basically part of some larger distributed system. Okay, and this evolution has continued. Now, all the wearable devices that you can buy are also computing devices. A watch is essentially a computer. Okay, you can now do fitness tracking with your devices. You can do all kinds of things with it. Okay, so wearables, which basically leads to healthcare, sensor networks, all of these essentially are now also parts of distributed systems, except that many of them are very resource constrained. You don't expect a watch to have the same kind of resources as you might have a server on the cloud. But nevertheless, it fits our definition of a distributed system. This is why I said it's a broad definition. If you have something with a processor and a network that talks to something else that has a processor and a network, that's a distributed system. So your watch will qualify, your phone will qualify, your TV qualifies, your car qualifies. All these are parts of a distributed system, so nodes in a distributed system. Okay. So these have now become pervasive. Okay, so that's essentially advances in technology. Okay, this is where we are today. We're starting from maybe 50 years ago when we started with a single machine to which many users were connected. Okay, that's a quick history of distributed systems. Let me pause here to see if there are any questions before I move on to talk about operating systems. Any questions whatsoever? Okay, let's move on. So I'll switch gears, talk about operating systems and its evolution. Okay, this is now all software related evolution. We are not talking about hardware anymore. Okay, so we'll start with uniprocessor operating systems. Okay, this is something you should know because you should have some exposure to a basic course in operating systems, but I'll start with uniprocessor operating systems. Okay, so these were early operating systems where the OS is designed to manage the resources on a single machine. Okay? The OS is a layer that is essentially arbitrating access to the hardware on the machine. Okay? It provides a logical interface to its user. It hides all the details of the underlying hardware. Okay? So this is also an example of transparency, although not in a distributed system context. Okay? When you create a file and you store it on your machine, okay, the OS is hiding details of where on disk it is stored. You don't say, put it on block 10 of my disk. You just say, here's a file, and the OS decides where it goes. Okay? When you start an application and create a process, okay, you start your web browser, you start some other application, you don't tell the OS, load it in this region of memory. It needs 1 gigabyte of RAM. You don't tell it all that. You just start it. The OS deals with all of that. It's hiding all the details of what is the RAM, where in RAM is your application stored, what is a disk, okay, where is your data stored. You get a file system interface, you get a process interface. All of that makes your machine much easier to use. You don't have to deal with the underlying details of the hardware. Okay, that's an advantage that the OS is providing to even uniprocessor operating systems. Okay. Now, the early ones essentially use what is called a monolithic architecture. What that meant is the entire OS was one large, think of it as one large application, except that it's a special application, one that actually controls access to the hardware. As opposed to user applications that are just applications you run, they're less privileged. They can't directly access resources. They have to go through the OS to access those resources. Okay? But nevertheless, the OS, or the kernel as we call it, okay, was monolithic in nature. Okay? One large piece of code that managed access to everything. Right? That's really not a scalable way, well, I shouldn't say scalable. That's not a good software engineering approach to writing any application. Okay? As the code base grows, if everything is just part of one bigger and bigger application, it's a nightmare to develop that code and keep ensure that it's bug free and so on. It's not modular design. Okay? That's not how you should write any large software system. And that is not how operating systems were written subsequently either. Okay? So they adopted many ways to make this monolithic architecture modular. Okay? I'm going to talk about one and just mention the other one briefly. Okay? So microkernel approach was one example of how you made the OS more modular. Okay? What's a microkernel approach? So in a microkernel approach, as the name suggests, what is actually the kernel of the OS is a very small component. Most of what you put in an OS, they're pulled out of the OS, and then they ran them as user processes. Your file system was essentially an application that ran on top of the microkernel. Okay, your memory manager was an application. It's a real process that ran outside the actual OS kernel, outside the microkernel. And so was the CPU scheduler and so on. So this was essentially a bare bones kernel that provided good inter-process communication. Okay? It allowed all of these components to communicate with one another. Okay? Normally, all of this code would be in here. Okay? You essentially pulled it out to make it modular. Okay? This gave rise to what was called a microkernel OS. Okay? Bare bones kernel, most of the OS functionality runs as processes, and then processes communicate to achieve the OS tasks. That is one way of designing an OS. Okay? Now, it's a highly modular way of designing an OS, because if you want to make modifications to the file system, you only need to touch that process or that code, that program is essentially providing file system functionality. You don't need to worry about what else is in the kernel. Okay? As opposed to touching a monolithic kernel where you might need to know a lot in order to actually make changes to something. Okay, so it was modular. It was more, people said it was more secure, because if there is a bug in some part of the OS, only that component gets impacted. Because if you have a monolithic kernel that has a bug and you exploit that bug, you can take over the OS, you basically can take over the machine. Okay? Here, you can essentially, if there's a bug in your file system module, you can only impact the file system module, not the memory. You can't go and corrupt memory, for example. Okay, so it has better security principles. Questions? Yes. Okay, question is in the microkernel picture on the slide here, are each of these boxes multiple kernels or is that one kernel? That's the question. So in the microkernel architecture, the OS is essentially the collection of what is called the microkernel and these modules which are running as user level processes. It's not that this is one kernel and that's a different kernel. That's not what we are talking about. Okay? It's essentially, this is the whole OS, except that you split the OS into pieces. Okay? Each piece runs as its own process and they communicate. In normal monolithic kernel, you will basically have a box that essentially is that box, and all of these are essentially is code or objects within that. I shouldn't say object, but it's code that resides within the OS itself. Okay. Any other questions here? Okay, so this was a good way of designing your operating system, but there was a big drawback of designing it this way. Any thoughts on what that could be? Yes.
Communication can be the bottleneck between.
Okay. So as you can imagine, there's a lot of communication that has to happen between all of these modules for the OS to achieve its task. To start a new process, you have to essentially send a message to the memory module saying, give me some RAM. And then you might have to have all kinds of coordination. Okay? Now, this message passing actually kills performance quite a bit. Okay? Because what was a function call in a monolithic architecture essentially became inter-process communication, became a message that has to go between two processes, orders of magnitude slower. If making a function call is very fast, everything is already in one address space, you just call a function within your program. That's very fast. Now saying I want to send a message to another program and have it do something, That's much slower. Okay? So the OS designers designed monolithic architectures. They said it's more secure. Then suddenly you had a performance problem. Things became really slow. Users are not happy if you give them a brand new machine that runs more slowly than their older generation machine, just because it has a fancy new OS architecture that the users don't really worry about. They just want good performance. So what happened as a result was your OS designer said, let's put some functionality back into the OS. Okay, just for performance reasons. Okay, but not everything goes back in. Some things still stay out, some things goes back in. But now you have some sort of a hybrid between a monolithic architecture and a microkernel architecture with one difference. Okay, they did adopt some modularity principle. So although the file system module may go back into the kernel, it still is a module that has well-defined interfaces. So you can only make changes to that module without worrying about the rest. Okay? You can load these modules on demand and whatnot. So it retains some software engineering benefits, but for performance reasons, somehow that code went back into the OS. Okay? Now, early versions of Windows essentially went from a monolithic architecture, okay, to a microkernel architecture. There was at one point something called Windows NT, which I don't know if any of you have even heard of, let alone used, but that was the Microsoft's attempt to design Windows using a monolithic architecture. Okay? The earliest version of Mac OS X also used a microkernel architecture. In fact, both Windows and Mac OS used the same microkernel architecture that was based on a research project, okay, that was designed at CMU many years ago. So they took those ideas, designed commercial versions. Performance was a problem. Then they started saying, let's put some functionality back. Okay, so the core functionality went back in. Okay, there are still microkernels out there today that you run for a variety of security reasons, but commercial operating systems took a step back and went back to a monolithic but modular design for designing operating systems. Okay, so let's move on a little bit. So that was still all unikernel, I mean, not unikernel, processor operating systems. Okay. Now I'll talk a little bit about distributed operating system in the 5 minutes we have left. Then we'll continue next time. Okay. So what is a distributed OS? Okay, this is an OS that's designed essentially to manage multiple machines. A uniprocessor OS is managing a single machine. Okay. Now what if you have a cluster? Okay. If your OS can actually manage multiple machines, that's called a distributed operating system. Okay. It's essentially used to manage a collection of machines. Okay. Now importantly, there are many flavors of distributed operating systems, and what flavor it is depends on what type of transparency it provides. Okay. The pure version of a distributed OS essentially makes the presence of multiple servers transparent. The OS runs on n machines. N is the size of your cluster. Okay. When you log into a machine, you don't actually see n machines. You just see a single large logical machine. The fact that there are n machines itself is hidden from the user. It just looks like a pool of resources. The fact that there are multiple machines underneath, when you start an application, which machine it runs on, all of that is hidden. Okay, this is called a pure distributed OS. Okay. Now, not all OSs actually behave that way, okay, but that is essentially what a distributed OS will actually look like. Okay. So it provides various types of transparency. The most important one is that it hides the fact that there are multiple machines. Okay. As opposed to not hiding it, which means that you have a collection, you have to SSH into a specific machine and run your job there. That's an example where you're not hidden anything from the user. Okay. That is what we'll call a networked OS, but not a distributed OS. It allows you to network and connect to the machine, but it's not hiding the details. You can still access a specific machine and run application. Okay. So that's a distributed OS. Okay. And as I said, there are different levels of it. The most tightly integrated one is, or a tightly coupled one, it's called a distributed OS. It essentially manages a set of machines, hides the presence of multiple machines. Okay. And then one step below that is a network operating system. It still allows you loosely to manage multiple machines, but it doesn't necessarily hide anything from the user. Okay. All of the OSs you access on your laptop and servers, are actually network operating system. Okay, because they allow you to manage one machine, they allow you to work with other machines, they're networked. Okay, they're network functionality, but they don't actually necessarily hide lots of the resources that a distributed OS will hide. Okay? And then there is something called a middleware OS, which takes a network operating system, it adds a software layer on top that tries to behave like a distributed operating system. So you take a network OS, you take Linux, Windows, Mac OS X, you run this layer on top, okay, and then all applications that run on top essentially see a more logical collection. Okay? So it'll take a network OS and make it behave or look like a distributed OS. So these are all flavors of distributed operating system. I think we had a picture somewhere. I'll come back to this. Okay, so this is an example of a distributed operating system where you have your uniprocessor kernels. Now this is a distributed OS kernel, okay, that you built, and everything about this just sees one large machine, one logical machine. You don't actually see that there's a machine A, B, and C above this layer. You just see a logical machine. Okay, that's a distributed OS. Okay, there's something called MOSIX, which is a flavor of Unix that gives you this abstraction. As an example, okay, here is our network operating system. This is basically Linux, Windows, or whatever else we use today. Okay, they are not giving us that abstraction. You essentially have machine A, B, C. You have your core kernel, your network functionality that allows you to do SSH, communication, TCP/IP, all of that is here. And then applications run on top, but they do see the presence of A, B, and C. Right? So you essentially access a specific machine, you communicate with a specific machine, and so on. Okay? That's an example of network OS. I'm going to show one more picture and then we'll stop. Okay, which is essentially our middleware. So this is taken a network OS. You have a middleware, which is a software layer that runs on top. And then above that, you basically see a single machine abstraction. Okay? So this takes commodity OS and still makes it look like a distributed OS. Okay, so we are 2 minutes over time. So we are going to stop here today, continue next time. Okay.